In this video, we're going to explore the concept of a paired t-test, which is also known as a dependent t-test. So a paired t-test is a statistical procedure that's used to determine whether the mean difference between two sets of observations is zero. So in a paired t-test or a dependent t-test, each subject or entity is usually measured twice, resulting in pairs of observations. These measurements could be taken from the same group at two different times. So we could look at an example of measuring someone or some individual before and after a treatment or an intervention, or under two different conditions. Perhaps there's seasonalities that you want to explore, so between the spring and fall, or they are matched subjects in two different groups. And when they're matched subjects in two different groups, typically there's some character trait or phenotype that you are matching between the groups, but we can also just look at it as the same individual measured at two different time periods. And importantly, the paired t-test accounts for the fact that the observations are not independent, but instead are linked in pairs. Okay, so when we look at our paired t-test, we have our null hypothesis. So our null hypothesis, our H naught, is simply saying that the mean difference, that's this mu subscript d, our mean difference is equal to delta zero, otherwise known as zero. So we can also set our alternative hypothesis. So HA in this case could be that the mean difference does not equal delta zero. It could be that the mean difference is greater than delta zero, or it could be that our mean difference is less than delta zero. It really depends on the type of question that you're seeking to answer. We then have our t-statistic. So our t-statistic, probably redundant that we would calculate a t-statistic in a paired t-test, but our t-statistic at n-1 degrees of freedom is equal to the observed mean difference minus the expected mean difference, which is 0, divided by the standard error of the mean difference. Okay, the SE d bar. Our confidence interval is simply equal to the estimate of the mean difference plus or minus our t star at n-1 degrees of freedom times our standard error of d bar, or the mean difference. The standard error, so SE d bar, is still equal to the standard deviation of our sample divided by the square root of n. That absolutely still holds true. We have to be cognizant of how we're getting that information, because you may need to add and subtract random variables from each other. But if you're given the standard deviation of the mean difference, then you can calculate the standard error relatively straightforward. So let's go ahead and look at our question here. So a small company has adopted an employee-athlete program to encourage their employees to be physically active with the intention of boosting employee productivity. To measure the difference in productivity, the company measures the average number of keystrokes per hour of 23 employees before and after the 5-minute per hour employee-athlete program is instituted. The data is followed for keystrokes per hour. So a nice clue here is right here in the question is saying that they measured the average number of keystrokes of 23 employees before and after. So when you have kind of terminology that says before and after, you can start thinking that you might be looking at a paired t-test. Nicely, the question has given us a lot of information. They've given us the measurements before and the measurements after. So we have a mean of 1497.3 before with a standard deviation of 155.4 and a sample size of 23. After, we have a mean of 1,544.8, a standard deviation of 136.7, again with the same sample size of 23. Nicely, this question isn't going to make us do or calculate the difference. They've given it to us, so we have the difference of after minus before. So another way of looking at this is the expected value of after minus before is equal to the expected value of after minus the expected value of before, right? We've done that before. They've given us our standard deviation of the difference, so the SD of after minus before. That's given to us right here, and they've given us an N of 23. Okay? If they didn't give you this information, of course you could calculate it yourself. You can go back to previous videos on adding and subtracting random variables from each other, and you can calculate all of those variables on your own, but it's nice that the question has given it to us. So the first part in A, the question is asking us, is there evidence to suggest that the program increases productivity? State your hypothesis clearly. So our hypotheses are as follows. So our H naught, or our null hypothesis, is going to be that the mean difference is equal to delta zero. Okay? Meaning that there is no difference between the groups. Our alternative hypothesis was going to be that the mean difference is greater than delta zero. Now the reason we're saying it's greater than, and we're not, so not HA does not equal zero, is because the question is saying, is there evidence to suggest that the program increases in productivity? Okay, so when we see increases, we're thinking of a one-tailed test. In this case, increasing productivity would be greater than zero, so our after minus before would be greater than zero. So our alternative hypothesis is going to be that the mean expected difference is greater than zero. So mu d greater than delta zero. Okay, so now that we have that, let's look at our t-test. So our t at n minus 1 degrees of freedom is equal to the mean difference minus delta zero divided by our standard error of d bar. Now, the question has given us our standard deviation, but it has not given us our standard error. So let's go ahead and calculate our standard error. So our SE d bar is equal to the standard deviation divided by root n. So this is equal to 122.8 divided by the square root of 23. I can do that a little bit nicer. The square root of 23. So we'll do the square root of 23. Store that in my calculator. 122.8 divided by the square root of 23, which gives us a standard error. So SE d bar is equal to 25.6056. We'll just put 4 decimal points. So that means that t at 23 minus 1 degrees of freedom is equal to our mean difference, which is 47.5. 47.5 minus 0 divided by 25.6056. So this is t at 22 degrees of freedom is equal to 47.5 divided by 25.6056. So t at 22 degrees of freedom is equal to 47.5 divided by 25.6056. Gives us a t-statistic at 22 degrees of freedom of 1.8551. So now we have to ask ourselves whether or not we can accept or reject the null hypothesis, or in this case, it's failed to reject the null hypothesis, not accepting the null hypothesis. It would be a failure to reject the null hypothesis. So let's take a look at what this is doing. So let's just draw our t-distribution, nice thick tails. What we have is we have an observed t, so this is t at 22 is equal to 1.8551. Now the question is what is the probability that the area to the right is? So let's go ahead and let's look up a t critical, so at say 0.05 or 95%. So in this case, what we're going to look at is we're going to look at our one-tailed cumulative probability. So that's right here at 0.05 in one tail because we're doing greater than, so we're doing a one-tailed test. And then we're going to go down to 22 degrees of freedom. We're going to trace our finger across, and we're going to find our value here of 1.717. So our t critical is 1.717. So we can put this on our graph here. So this is t star, and this is 1.717. So therefore, the probability that t is greater than 1.8551 is going to be less than the probability that t is greater than 1.717. So therefore, we reject the null hypothesis in favor of the alternative. In other words, there is sufficient evidence to support the claim that the program increased employee productivity. Okay, so we've done A. Now we're going to look at and say, okay, give the 95% confidence interval for the mean change in productivity as measured in keystrokes per hour. So B. So our equation for our confidence interval is going to be d bar plus or minus t star at n minus 1 degrees of freedom times our standard error of d bar. Well, we know what d bar is. That's going to be 47.5. 47.5 plus or minus t star at 22 degrees of freedom times our standard error that we've already calculated. We calculated that right here to be 25.6056. And now we have to ask ourselves, well, what is our t critical? So although we've already found a t critical value, at a 95% confidence interval, remember what we're looking for then is an area in each of these tails to be 0.025, right? Which means that this is the central 95% of our observations. So we need to go back to our t-table, and we're going to look up our t-table. And before, we picked this one, but in this case, we're looking at a two-tailed distribution. So we're going to go right here, and we're going to go to 22 degrees of freedom, which gives us a t star of 2.074. Okay, 2.074. So plus or minus 2.074. So 47.5 plus or minus 2.074 times 25.6056. So then this becomes 47.5 plus or minus 2.074 times 25.6056 gives us 53.1060, So 47.5 minus 53.1060 gives us negative 5.606, and 47.5 plus 53.1060 gives us a value here of 100.606. So that is our 95% confidence interval. Okay. And then question C here says, explain any difference in the results of A and B. Well, in A, we rejected the null hypothesis in favor of the alternative. And in B, our 95% confidence interval includes 0. So if we have our number line, and this is 0, we have observations then between negative 5.606 and 100.606, right? This was our 95% confidence interval, and of course it includes 0 and values less than 0. And in the 95% confidence interval, what this is saying is that it's possible that there was a decrease in productivity. So what does this actually mean? So note that the confidence interval in B does contain 0. So it would look as though we cannot reject the null hypothesis. So when you have a confidence interval that includes 0, typically you might say you fail to reject the null hypothesis. However, we do notice that we rejected an A. And importantly, the difference is that in A, we rejected the null hypothesis at a 95% significance level. And in B, there's a 95% probability of being within that confidence interval. So in other words, saying there's a 2.5 probability on either side, right? Just like how we looked at that right here. 2.5% probability on either side. So what we can say is that there's a 97.5% probability of being above the lower limit of negative 5.61. So let's just visualize that for a second, because that's perhaps a little confusing. So we have our t, and what we're saying is that we were centered around 47.5. And we got this value here that was saying negative 5.61, and the other one was 100.606. This was 5 point. We'll just keep it consistent with what we did. 606. So when we say that there's a 95% probability of being above the lower limit, that is what we're saying. The area to the right of this lower limit is equal to 97.5%. Now that makes sense because we know that the area to the left is equal to 0.025. Okay, so 1 minus the probability that d bar is less than negative 5.606 is simply equal to 1 minus 0.025, which is equal to 0.975. So in other words, we have a 97.5% probability of being above the lower limit of the confidence interval, and we are therefore 95% sure that there's a productivity improvement, and that's from part A. So we're 95% sure that there's a productivity improvement from part A, but we are not 97.5% sure. Okay, so this is just a degree of certainty that we're incorporating into the question here. So we are 95% sure that there's a productivity improvement. That's what we calculated in A, but based on our confidence interval, we are not 97.5% sure.
That's it for this video, but if you found that it helped to make statistics easy, consider showing your support by giving the video a like. And if you still need more help with statistics, then consider subscribing to the channel if you haven't already. I look forward to solving many more problems with you next time.